This is Honors Algebra 2 Pre-Calculus. We're doing 10.8 in Pre-Calc, which is polar graphing. So in example 4, we're going to do the last one of these that I'm going to encourage you to graph by hand, because again, in the real world, you would just not do a lot of polar graphs by hand. It's a good skill to be able to plot points if you have to, but it is not a realistic thing to make you do these super incredibly detailed polar graphs by hand. That's just silly. So we're going to do this by hand, and then we're going to, in the next video, spend some time talking about some special polar curves that look super awesome. But again, you'll be able to graph them on your calculator. So what I've done here is I've put all the points in the unit circle from 0 to 2 pi, and we're going to graph r equals 3 cosine 2 theta. So I'm going to go ahead and plug these in. I'm not going to do a lot of work when I do it. I'll talk you through it, but we just don't have that much space. So remember, what I'm plugging into is 3 cosine of 2 theta, right? 3 cosine of 2 theta, in case that's not super easy to see on the board. Okay, so 3 times cosine of 0 would be a 3, right? 3 times cosine of 2 pi over 6 is the same as pi over 3. So that's 3 times cosine of pi over 3, which would be 3 halves or 1.5, right? 3 times the cosine of 2 pi over 4, well, that's the cosine of pi over 2, so that's going to be a 0. 3 times the cosine of 2 pi over 3 would be a negative 3 halves, right? 3 times the cosine of pi would be a negative 3. 3 times the cosine of 4 pi over 3 would be a negative 3 halves. 3 times the cosine of 3 pi over 2 would be a 0. 3 times the cosine of 5 pi over 3 would be a positive 3 halves. And 3 times the cosine of 2 pi would be a positive 3. 3 times the cosine of 7 pi over 3. Well, 7 pi over 3 is the same spot as regular pi over 3, so that would be 3 halves, right? Because that's 7 pi over 3, just to be clear, 7 pi over 3 minus a full circle, which would be 6 pi over 3, gives you a regular pi over 3, right? 3 times the cosine of 5 pi over 2. Well, 5 pi over 2 is the same spot as regular pi over 2. So essentially, we're just doing another lap around the circle. So really, we shouldn't necessarily have to bother with this, because if you're noticing, we're getting exactly the same values, right? This is the same spot as this. This is the same spot as this. So I'm going to get exactly the same values here, right? Like these are all the same spots, right? And by the same token, this would be 10 pi over 3, and 10 pi over 3 is definitely the same as 4 pi over 3, right? So that's going to be the same values, right? So we're going to end up getting the same spots, right? Cool. Do I agree with that? I feel like I do. 4 pi over 3 would have been an 8 pi over 3, which is the same as 2 pi over 3, and this was a 2 pi over 3. Yep, totally agree with it. All right, so anywho, point being, I didn't end up having to do the second half of the table because, and you actually could have predicted this, because the period of cosine of 2 theta is 2 pi divided by 2, meaning that we should get a full period in the pi window, right? So we should get a full period in the pi window. So let's plot our points now, okay? So when I plug in, all right, so when I plug in 0, I get 3. Oh, sorry, inching. Say 0, I get 3, which is here, right? When I go to pi over 6, I get 1.5, so 1.5. And at pi over 4, I'm back to 0, right? Then at pi over 3, which would be here, I go to negative 1.5, so 1.5 in the opposite direction. At pi over 2, which would be this line right here, I go backwards 3 units, so I'm here, right? And then at 2 pi over 3, which should be right here, I go backwards 1.5 and land here. And then at 3 pi over 4, which is here, I'm back at 0, right? So just to be clear, this is what's happened. I went from here to here, and I made this loop, okay? Now, I'm back at 0, so I'm here. I'm back at 0. At 5 pi over 6, which is here, I go to 1.5. At pi, I go 3 units, which is here, right? So I'm now going this way, right? So I've done all of these. At 7 pi over 6, which is here, I should be at 1.5, which is here. And then at 5 pi over 4, I'm back to 0. So I've done these guys. Then I'm going to go to 4 pi over 3, which is right, like this line right here, but I'm supposed to go backwards 1.5, so that's here. At 3 pi over 2, I'm supposed to go backwards 3 units. Well, that means go the pi direction 3 units. At 7 pi over 4, which should be here, I'm at 0 again. I think I skipped. Oh, sorry. At 5 pi over 3, I'm at negative 1.5, which is here, and then I'm back at 0. So this looped this way, and I think we can all predict that what's going to happen is this last loop here. So at 7 pi over 4, I'm at 0. At 11 pi over 6, I'm at 1.5, which is here, and then I go to 2 pi comma 3, and there you have this nice like flower shape that has 4 petals. So if I show you what this graph looks like on my calculator, and I'm going to change my window to be closer to the window I graphed by hand. So I'm making my window go up to 4s. Okay, so if I graph this, you're going to see that I have this nice 4-petaled shape. Now you might say, hey, that's weird, the petals don't look like they're the same size. Remember, that's because the whole zoom square thing. So if I do zoom square, which is 5, it's going to look like the petals are all exactly the same size. So I have these 4 petals. So essentially what we're going to talk about in the next video is that there's a whole bunch of really cool polar graphs that you can do that look like sort of these flower shapes. This is called a rose curve. There are different kinds of rose curves. There's lots of different curves. So we're going to walk through those in the next video.